Okay, for this video I'm going to be focusing on dispersion. Dispersion is the separating of polychromatic light into its separate colors or wavelengths. White light is made up of um, all of the colors of the rainbow. And so if we look over here at this very famous album cover of Pink Floyd's Dark Side of the Moon, we have white light traveling in, let's say, air here, and it strikes this glass triangle. We call this a prism. And when it goes into that new medium, it refracts. And so it changes its direction and changes its speed. And then it leaves that glass prism and it refracts again. And it's this double refraction pattern that actually changes the direction and the speed of each of these individual colors of the light, the white light, into the individual components of the white light. So we get the color of the rainbow. So it uses refraction to bend light at different angles to separate visible light into its various components. Here's just kind of another animation here that we've got going on, where we have red up on top and then violet on the bottom. And notice that the red has the biggest wavelength and the violet over here has the shortest wavelength. And it's in order of biggest to smallest wavelength. We'll discuss why that is the fact in just a moment. So again, if we look at this picture here, the index of refraction ultimately depends on the wavelength of light. So every color has a slightly different speed within the substance. Let's explain that statement here. The index of refraction, based on the equation I gave you earlier in the unit, is a ratio between the speed of light in a vacuum and the speed of light in that particular substance. Well, the speed of light is dependent on the frequency and the wavelength. So I could rewrite this as the frequency of the light in the vacuum times the wavelength of light in a vacuum divided by the frequency in that new substance times the wavelength of light in that new substance. Well, frequency is going to remain the same here, so these frequencies cancel out when light goes into a new medium. So really the index of refraction is based off of the wavelength change, or the ratio between the wavelengths. And each individual color has a different wavelength, so it has a slightly different index of refraction. Specifically with red having the biggest wavelength, so it has the smallest index of refraction. And violet having the shortest wavelength, so decreasing this, and giving it the biggest index of refraction. So the red light with the longer wavelength travels faster than the violet, shorter wavelength, and bends less in the prism. So the red actually appears up on top of the pattern. And as I mentioned earlier, light is dispersed in order of decreasing wavelength. Let's look at the interference of light. Light, as I mentioned earlier in this unit, can behave as a wave. So we're going to focus on the wave behavior of light and how we actually prove that light behaves as a wave. Before we do that, let's just do a couple reminders here. When a crest or a trough and a trough meet in the same medium, constructive interference will occur. And remember, constructive interference, that's when the wave has a larger amplitude. The path difference between these two sources is a full wavelength. When a trough and a crest meet in the same medium, that results in destructive interference. The path difference between the two sources is a half a wavelength. Also, let's review what the bending of light around a barrier is called, and that is known as diffraction. And what diffraction looks like is that we have a nice wavefront coming in here on the left, and we got this little barrier. When it goes through, it doesn't just pass through just right there, it actually bends around and fills up the whole right side on the other side of this barrier. Now, a couple relationships with diffraction, or the amount of bending of light. If you decrease the size of this opening, making it smaller, that causes an increase in the amount of diffraction, or the amount of bending. Let's take a look at these two animations that show that. So on the left here, I've got a large opening, and the light's coming through, and notice that it doesn't diffract too much. It doesn't bend right here because the opening's bigger, so it doesn't have to bend as much around the barrier. On the other hand, if I make that barrier very small, decreasing the size of the opening, now we get a much greater amount of diffraction or bending of the wave around the barrier. The other relationship we should remember for diffraction is increasing the wavelength causes an increase in the amount of diffraction of the pattern. So if I have the wavelength more spread out on this side, it's going to cause more diffraction on the right side after it goes through that barrier. Now, if we look at the interference pattern of two sources traveling in the same medium, we have a combination of constructive and destructive interference. So I've got over here one wave being generated and another wave being generated. And let's say these thin lines represent a trough and the thick lines represent a crest. So if I look at this specific point, let's say the red dots right here, notice that I've got a crest, or I'm calling this a trough from this source, source 1, interfering with a trough from the second source. So this would result in constructive interference. And same with this one. I've got a crest from source 1 interfering with a trough from source 2, crest from source 2, so we would have constructive interference going on here. So this whole side sets up constructive interference. On the other hand, if we look at the blue dots, this would represent destructive interference because I've got a crest and a trough from each one of those sources colliding with each other. So let's take those two ideas of interference and diffraction, and this actually is used to prove that light behaves as a wave. Thomas Young was an English physicist, and he proved that light was a wave by using the double slit experiment. It shows that light exhibits diffraction and forms an interference pattern when shown on the two closely spaced slits. So basically what he did is he took monochromatic light at one specific frequency, and shined it to these two very narrow slits. Well, when the light went through this opening, it diffracted. He found that it diffracted. And same for this one. And he could prove it diffracted because what he saw over here on this screen that captured the light was an interference pattern. If light behaved as a particle, in theory the light would only end up right here and right here, directly across from the openings. But he saw parts where we had a bright fringe, so light was actually being shined here, and then above and below that, you had dark fringes. Where we have a bright fringe going on, that's where a crest from the wave up on the top here is interfering with, let's say, a crest from the other one, and that would result in constructive interference. And the other part up above and below, you saw a dark spot, and this would indicate that there was destructive interference going on because these two waves diffracted around these openings, setting up two waves traveling the same medium, and they were half a wavelength apart. And then we also had constructive interference going up above. So constructive interference with like a crest and a crest meet, and the destructive interference was like when a crest and a trough met. Let me show you this again, just kind of another format here using this simulation. So what I have is, let's say, a light source, and I've got these two narrow openings right here, and I've got a screen over here to capture its light. Now, if light was just a particle, the light would only travel through this opening and through the second opening and land up right here. But what Thomas Young noticed when he turned on the light source, shined it through, there was he saw a bright fringe right here, a dark fringe up above and below that, and then another bright fringe. And he concluded that this would only occur if light was bending around each one of these openings, setting up basically two sources of light, and those two sources were interfering with each other, setting up this interference pattern on the wall here. Right. Now, there's an equation that goes with this, and the equation looks like this. Lambda over d It's equal to x over L. Now this is not on your reference tables. We're going to do a couple activities and labs in class to focus on this equation, but I'm not going to make you responsible for actually using this equation on test or quiz. Well, d, let me go over each one of these variables here. D represents the distance between those two slits. Lambda represents the wavelength of the light source. And x represents the distance between that center fringe that you saw, that bright fringe, and the next bright fringe. In between there was a dark fringe. L represents the distance from the screen and the slide, or the double slits in the screen that's capturing the light. One other thing I want to mention with interference of light, and this is, again, something that I'm not going to put on a test or quiz, but I just want to discuss it briefly here. So if you've ever seen a pattern after you maybe like spilled some gasoline on some wet concrete or asphalt on the ground, you get this cool rainbow pattern. And this is because of the interference of light. What happens is white light, comes from up above, let's say the sun here, and it goes through that oil or gas what you spill. Some of that oil reflects off of it, straight in this line right here, and then some of it is going to refract and go into the new medium. Well, that light that goes into the new medium is going to bounce and reflect off of the water that's below it. And then what will happen is that will again refract. And depending on the depth of this oil spill, the gas that you spilled there, certain colors of light will cancel out because we have two waves traveling the same medium, and certain waves will cancel out, and that white light will only show certain colors depending on the depth. That's why you see this pretty rainbow pattern. Like if you've ever blown a bubble, if you look at it at just the right angle, sometimes you can see that you get the rainbow inside the bubble there. Again, that's because of the different thicknesses and the portions of the bubble that you've blown. That concludes the section.